Today, we're going to talk about electromagnetic radiation and how it gets started. And then next week, we'll talk about the interaction of light, of electromagnetic radiation and matter, which is a very rich topic, and we won't spend anywhere near enough time on it. And then the last day we'll talk about sparks, which is a good review of just about everything we've done during the semester. Last time we developed the last piece of Maxwell's equations in their full formal glory. Maxwell's equations describe all possible configurations of electric and magnetic field. In space. And there are four of them. The first is Gauss's law, with which you're familiar. So the sum of the electric flux over a closed surface tells us the amount of charge inside the surface. So this is Gauss. And Gauss's law for magnetism says if you add up the magnetic flux all over a, whoops, there's a dA here. Then we get 0 because as far as we know, there aren't any magnetic monopoles. So there's no magnetic charges like souths without norths or norths without south. We have Faraday's law, which says that a time-varying magnetic field makes a curly electric field. And we write that analytically as the EMF is equal to the rate of change of magnetic flux. But if we amplify this and write out these terms, what we're getting is the integral of the electric field around a closed path. So E dot dl around a closed path. It is the derivative, the time derivative of the magnetic flux, which of course is B dot n hat dA on the surface bounded by the path. And we saw a little bit that there are two parts of this, that usually it's the magnetic field that's changing, so that's where the derivative comes in. And the way we actually evaluate this integral is we evaluate the B dot n hat dot product first, and then we can multiply by dA, the area, and then there's a time derivative there. And finally, the Ampere-Maxwell relation, which is Maxwell's extension of Ampere's law. So we have the integral of B dot dl around a closed path is equal to mu0 times the current, conventional current that pierces the surface stretched over the path, plus epsilon 0 times the time derivative of the electric flux. So we get a time varying electric field causing or being associated with a curly magnetic field of the usual kind. And we use these Maxwell's equations to show that a time varying magnetic field in space could produce a Curly electric field that itself was time varying if we varied it appropriately with time, which would then produce a time varying magnetic field. And so, these fields could sustain each other traveling through space, and indeed that is an electromagnetic wave. And we found that it had to be, it was if and only if this pulse propagates with speed c, where speed is the speed of light. And we saw that that a very simple configuration of this was simply a region of space where we had an electric field perpendicular to a magnetic field in this region. Traveling in a direction perpendicular to both of them, and that it so that the conditions for this working were that the magnitude of the electric field had to be c times the magnitude of the magnetic field in this region, and the relationship between directions was given by if we take the cross product of the direction of E and the direction of B, we get the direction of V. So this is directions. And that, in fact, is an electromagnetic wave. So what we didn't actually do last time is we didn't figure out, so we decided that this was a legitimate configuration of fields, that we could have this E and B propagating in some direction at right angles to each other, but we didn't figure out how we could get this started. And so the topic of today's discussion is, how can we generate this pulse or this wave of electromagnetic radiation, this electromagnetic wave? I want to show you a VPython program. And in this case, we're going to talk about the easiest way to understand qualitatively what's going on here is to talk about the concept of electric field lines. Now, this is something we haven't talked about in class because on the whole, this isn't a particularly useful concept. And it comes along with it sort of drags along with it a lot of misconceptions that we have to spend time dealing with. But in this case, it's a useful representation. So what is a field line? Well, what a field line is this. So here in our display, we've got a positive charge. And of course, the electric field points outward from the positive charge. And what we've drawn here is a little bit different from what we usually draw, in that we have vectors representing the electric field at different locations, but each of these is a unit vector. So the length of the vector does not have anything to do with the magnitude of the field, the strength of the field. It only shows the direction of the field. And so if we're only interested in directions of fields, then field lines can be a useful representation, although the way we make a field line is just to connect all these vectors in a line, and then it's almost not all that useful anymore because it doesn't tell you which direction it's going. So on the whole, not a terribly useful representation. However, in this particular case, it does enable us to see what actually happens and how we can generate electromagnetic radiation. So the electric field, due to a stationary positive charge, points away from the charge. And these unit vectors here, or these field lines, can represent the field of this charge. Let's see what would happen if we gave this charge a kick. So here's the same representation of positive charge sitting here making an electric field, which we're now representing by field lines, which are just showing connecting unit vectors. But what would happen if we accelerated the charge briefly downwards? So I'm going to run this program. What's going to happen in the program is we're going to give the charge a kick. So it's going to have a brief acceleration, and then it's just going to coast downward. Okay? So let's watch what happens. So we gave it a very brief kick downward, and now it's just coasting at constant speed downward. Well, this affects the pattern of electric field that an observer sees here. So let's do this again and think about what's happening. So what's happening here is that as the charge moves downwards, so the top dot here is the original location of the charge, and the, let's get the chat window here. The bottom dot where the little lines coming out, it is the current location of the charge. And now the electric pattern of electric field in space has a very interesting sort of character. Because as the charge coasts downward, in its new position, the field due to this charge certainly points away from its current location. But some observers haven't found out yet that it moved. If you're far enough away, so you're, for example, over here at the very right of the screen, you don't, information that the charge is moving, it hasn't reached you yet, because the information about electric field can only travel at the speed of light, and you're far enough away that it just hasn't gotten there yet. So what do you detect with your little proton on a spring? Well, what you detect is an electric field pointing to the original location of the charge, not to its current location. Now, people who are observers who are closer don't see that. They see the electric field that's due to the slowly moving charge, the moving charge here, pointing away from the charge. But observers who are too far away for that information to have reached them still detect an electric field pointing to the original location of the charge. Well, there must be a discontinuity when this happens. And so let's put our cursor right here. So we're an observer standing on this horizontal field line to the right of the charge's original location. And let's see what happens. So we see a field pointing away from the original location, away from the original location, away from the original location. Oh, we see a field pointing down, and now we see a field pointing at the new location of the charge. And it's this kink, this sort of downward piece of the field line that is the radiation emitted from this charge. Now, this is a kind of a simplified animation in that we're assuming here an instantaneous brief acceleration of the charge. So there's only this one very short pulse that, came out here. And so it's this what we call a transverse electric field here. That's a characteristic of the radiation emitted from the charge. So what does this look like in 3D? So here's a charge that's going to be, when I click, the charge will be accelerated. It's a positive charge. It'll be accelerated very briefly downward, and then it's going to coast. And we're not going to draw the ordinary electric field that just comes out radially from this charge. We're only going to draw in this animation the electric field in this little kink, this pulse, due to the acceleration. And what happens is a little bit complicated looking. You see this pulse of radiation that's perpendicular to the direction of acceleration, spreading out at the speed of light. And here in this animation, we also saw both the electric and magnetic fields. So I'll run it again and then pause it when we get here. So this is what, if we were standing right here, this is what we would see. We would see an orange electric field going up, a blue magnetic field going perpendicular to it. And the direction depends on where the observer is. So if we're perpendicular to the acceleration, we see it going straight up. If we were up here at the top, it's going at an angle. And if we're in line with the acceleration of the charge, we see absolutely nothing. So this radiative pulse of electric and magnetic field spreads out, and the direction of these fields, so it spreads out in every direction, and that's important. Okay, so we need to note that in every direction except along the line of acceleration, this field, this pulse of radiative electric and magnetic field is spreading out. And its direction depends on, the direction of the fields depends on where the observer is, where the observation location is. Okay. So what if the charge was a negative charge? So let's accelerate an electron downwards. We get the same thing, except that the fields are pointing in the other direction. So before, the electric field was up and the magnetic field was to the left in front, and now it's down and magnetic field's to the right. So let's do that one more time. So the sign of the charge also is important in determining the configuration of the fields. A slightly easier, a simpler representation might be to just take a 2D slice through this. So here is a 2D slice. So we're just going to look in the plane of the page here. And we've kicked the charge downward. And there's a lot of arrows here. So the orange is the electric field. The cyan is, of course, the magnetic field, which is pointing into or out of the page, we can see here. The yellow arrow is the brief acceleration. The green arrows are just our friend R. They're the vector from the source to the observation location. And the little magenta arrows are a vector in what's called the direction of propagation of the wave, of the pulse. That's the direction the pulse is moving. And you can see that in this case, that direction is actually just the same as R. And again, we see that that the magnitude of the electric field is largest along a line perpendicular to the direction of the acceleration, and the magnitude of the fields is actually 0 along in the direction of the acceleration. So we'll run that one more time, and that's just the 2D slice through that complex 3D pattern. Okay, so let's be quantitative about this. Okay, so if it's an electromagnetic pulse, doesn't the electric field have to change with time? And the answer is, it is varying with time to any observer. So let's consider a positive charge that was accelerated downward. And we saw that along a direction like this, we had a pulse which had an electric field up and a magnetic field out of the page, and the pulse was traveling that way. And so let's put an observer somewhere. Let's put our observer here. And let's think about what this observer sees as a function of time. So the observer has a proton here on a spring. So that's our detector. And what the observer is going to do is graph what they observe in terms of the transverse, this transverse electric field as a function of time. And so the pulse is here and the observer doesn't see anything, so they're detecting a zero electric field. And now the pulse gets to here and they're still not seeing anything. And finally the pulse gets to the observer, and the observer actually sees a non-zero electric field for a time that's the width of the pulse. If our acceleration lasted a little bit longer than an instant, then we'd have a pulse that lasted for some finite time. And now this pulse has traveled past the observer, so they're no longer detecting anything. So in fact, at the location of the observer, the electric field is indeed changing with time. And likewise, the magnetic field is changing with time, because if our observer tries to detect the magnetic field here, they'll get the same pattern. We'll get nothing until the pulse gets here, and then we'll get a magnetic field for a short time, and then. So what this observer sees is indeed a time-varying electric field. So at any location in space, this is happening. And we'll talk about some things that aren't just a single pulse in a minute. So the equation that actually describes this is the following. We have the equation for this transverse, what we're going to call the radiative electric field, this electric field in the radiation. So we'll call it the radiative electric field, is given by our familiar constant 1 over 4 pi epsilon 0. In the numerator, we've got a minus q a perpendicular over a c squared r. So let's look at this equation and see what's familiar in this equation and what isn't. So what's familiar? Well, we know what 1 over 4 pi epsilon 0 is. That's just the constant. Q is clearly the charge of the accelerated particle. So Q is charge of accelerated particle. C, that's just the speed of light. R, that's our familiar r, distance from source to the observation location. So the only thing that's weird in this is this A perpendicular. So what is that? So what is A perpendicular? So A perpendicular is the component of the acceleration that's perpendicular to the vector r. And it looks like for a positive charge here from this equation, the radiative electric field is going to be in the opposite direction from the direction of this A perpendicular. It is a projection. So let's draw a picture here and see what it looks like. So here we have a positive charge, and let's say that we were standing here. So this is our vector r, and the acceleration was downward. So here, A is perpendicular to r. Okay, so A perpendicular is just A. But at a different observation location, that wouldn't be the case. So here's our charge. Here's our acceleration. But now let's say we're standing here. So now our points like that. Well, what we want is the component of A that's perpendicular to R. So what we're going to do is we're going to draw an imaginary line that's perpendicular to R. And then we'll take the projection of A onto that line, the component of A that's along that line. So that would be a component of A on that line, and of course that would be the component of A parallel to R. And so it's this component of A perpendicular to R, or we could draw it a little bit differently if we wanted to. We could draw, here's R, here's A. We can draw our perpendicular line here, and so this would give us A perpendicular. So in this case, quantitatively, how would we calculate the magnitude of A perpendicular? We know its direction, but how do we get its magnitude? Well, if this angle here is theta, then the magnitude of A perpendicular is just going to be A magnitude of A sine of the angle theta. Yeah, you'd have to know the angle. So you need to know the direction of the acceleration and the direction of R, the vector pointing from the source to the observation location, in order to do this calculation. Okay, so let's see if we can answer a couple of questions, practice this a little bit. So we have a proton that's accelerated. So here's our proton, and it's accelerated in the direction shown by A here. And our observation location is P. And the first question is, what is the direction of propagation of radiation reaching this observation location P? So what does direction of propagation mean? Direction of propagation is the direction that this pulse of electromagnetic radiation is traveling to get to your observation location, right? So what's the answer? Okay, mostly ones, but we have some 7s or 8s. So let's just draw it, okay? So here's the source. And here's your observation location up at P. And so the radiation had to start at the source and it had to travel toward P to get to the observer. Yeah, so the radiation, so this is an important concept here, the direction of propagation. And it sounds like it's got a lot of big words in it, but it actually just means the direction from the source to the observation location. That's all it means. So 1 is correct. Okay, so the direction of propagation is straight up. Now with the same observation location, so the same observation location P, what is the direction of A perpendicular? Okay, awesome. You're definitely on it. So so this was our direction of propagation. So we could call that R, but we could also call it V. That's the direction of that pulse is moving. So we need a line perpendicular to that. And so in fact, the component of acceleration perpendicular to that is going to be on that line. So it is indeed 3, that's correct. Good. So now we know that the direction of propagation is up and the direction of the perpendicular component of acceleration, A perpendicular, is to the right. So given that, if you stand at location P, at observation location P, what will you observe? What is going to be the direction of the electric field that you're going to observe? Remember that the equation we have is E radiative equals a 1/4πε0 minus Q A perpendicular over C² R. Yeah, you're exactly right. So we have A perpendicular here. And because we have this minus Q here, Q is positive in this case because this was a proton. So the direction of the radiative electric field has to be opposite to A perpendicular. So when the electric field gets here, we're going to see radiative electric field to the left, opposite the A perpendicular, direction 7. Excellent. Now let's consider the same situation, but let's take observation location S. So if you're standing at S instead of at P, what for you is the direction of A perpendicular? Okay, so let's let's talk here. So there's several steps here. The first step is to draw the direction of propagation, which would be from the source to the observation location. So that's the direction of propagation, direction. And indeed, if we draw a line perpendicular to that, it sort of goes from 8 to 4, right? But now what we want is the component of the acceleration that's perpendicular, that the projection of this acceleration onto this line, or the component of A along that line. And what's the story here? Yeah, it's 0, isn't it? It doesn't have a component. So in fact, since A is parallel to V, A perpendicular is 0. What does that mean for the observer at location S? That's right. They're just not going to see, there's going to be no radiative electric field. They're not going to see this pulse of radiation come past them. So that's like standing at the top of the VPython program along the direction, or the bottom. Now, they will still see the ordinary Coulomb electric field, but they won't see this pulse of radiation go by. Okay, one more. So we have a proton accelerated now to the left. That line is supposed to be to the left. And so location S, what's the direction of propagation? So this is, yeah, that's right. So the direction of propagation is that direction. And you can tell what the next question is going to be. What's the direction of A perpendicular, right? Very good. So 8 is correct. We draw this perpendicular line here, and we find that the component of A perpendicular to that points that way. And so, of course, our next question is, what's the direction of the radiative electric field that an observer at S is going to see? Indeed, that's absolutely correct. So at S, what you'll pick up is a radiative electric field in that direction. Let's go back to here and do a quantitative calculation. So let's take and let's make it an electron. So here's an electron that's accelerated in this direction. And we have an observer over here at location R. And we know some values. So the values are that the magnitude of the acceleration, which is a very brief acceleration, is 2 × 10⁻17 meters per second squared. We couldn't accelerate that with that acceleration very long. Some issues with that. And the distance from the source to the observation location is 0.02 meters. And it's an electron. So let's find, what we want to find is the radiative electric field, the radiative magnetic field. And then we also want to find how does the magnitude of the radiative electric field compare to the ordinary just Coulomb radial electric field? So this is what we want to find out here. And we need an angle, as Jonathan pointed out. So this angle is 20 degrees. Okay, so the first thing we need is a perpendicular. So a perpendicular magnitude is just going to be the magnitude of A times sine of theta here. But let's see. That's not the right angle, is it? So actually, the angle, so a perpendicular is going to be that way. And so, oh, that is the right angle. Okay, so indeed, this is going to be a perpendicular. I drew it a little too big here. And so, so that's going to be 2 times 10 to the 17th meters per second squared times the sine of 20 degrees. If you're using glow script, remember to convert to radians. And so that's going to be 6.8 times 10 to the 16 meters per second squared. And so now the magnitude of the radiative electric field is going to be 1 over 4 pi epsilon 0, the absolute value of the charge times the magnitude of a perpendicular over c squared r. So we have 9 times 10 to the 9 Newton meters squared per Coulomb squared times 1.6 times 10 to the minus 19 coulombs, 6.8 times 10 to the 16 meters per second squared, divided by 3 times 10 to the 8th meters per second quantity squared, times the distance, which is 0.02 meters. And if we crank through that whole thing, we find that the magnitude of the, whoops, that should be radiative. The radiative electric field is 5.5 times 10 to the negative 8th newtons per coulomb. So not huge, but we have only one accelerated charge. This was an electron. And the direction of the radiative electric field, let's see here. So here's our observation location up here. We found that A perpendicular was up, and therefore, for a positive charge, the radiative electric field would be down. But since this is a negative charge, we're going to find that the radiative electric field goes that way. And now let's calculate just the ordinary Coulomb electric field, which is just going to be our 1 over 4 pi epsilon 0 q over r squared. So that's 9 times 10 to the 9th times 1.6 times 10 to the minus 19 divided by 0.02 meters squared. And we get 3.6 times 10 to the negative 6 newtons per coulomb. So at this distance, so at 0.02 meters, the ordinary Coulomb electric field is greater than the radiative field in that pulse. But what's going to happen if we get farther away? Notice that for the Coulomb electric field, it's falling off like 1 over r squared, but the radiative field is only falling off like 1 over r. So yep. So as we get farther away, the radiative electric field will absolutely be bigger. And so if we do this at 20 meters, we find that the radiative electric field that an observer would detect is 5.5 times 10 to the negative 11 newtons per coulomb. But now the Coulomb electric field is only 3.6 times 10 to the negative 12 newtons per coulomb. So E radiative is bigger than the Coulomb field, and as we get farther and farther away, that trend will only amplify. So at 200 meters, there are a factor of 100 different. All right. Questions so far about this? Well, the net, okay, so what would the net electric field at the observation location be? Well, it's going to be changing, for one thing. So here's our observation location. So let's say, and so if we drew the Coulomb field, we'd have, whoops, it's an electron. So we'd have the Coulomb electric field that way. So the net field is the net field. And so at that observation location, the field will be the sum of those two things. And so what the observer would see is mostly, for most of this time, they'd just be seeing the Coulomb electric field until the pulse passed. And so while the pulse is passing, we're seeing a net field that way. And then the pulse is passed, and so we no longer have that field. So it's, however, what's going to happen here is that the further away we get, the ordinary Coulomb field becomes negligible relative to the radiative field. And so that in fact, at a far enough distance, for example, if you're 200 meters away, it's a factor of 100 different. And so you may not even detect that Coulomb field. You would only really be sensitive to the pulse passing. Well, we know that in a pulse of radiation, we know that E equals C times B. These are magnitudes of fields. So the magnitude of B radiative is just going to be E radiative divided by C. So the radiative magnetic field that you'll see is 5.5 times 10 to the minus 8 newtons per coulomb divided by 3 times 10 to the 8th meters per second. So it's going to be something like 2 times 10 to the negative 16 Tesla. Not very big. but it's there. Now, if you think about the fact that an accelerated charge produces electromagnetic radiation, you might ask the question, what about atoms? So our simple model of an atom shows an electron orbiting a positive charge. And even if we take a slightly more sophisticated model where we know that it's moving in a spherical pattern and not just a circular pattern. So here's our electron. Let's say it's moving this way. Well, this electron is accelerated because its momentum is changing. So we have a dp dt perpendicular here at any point in the orbit. We've got this, and dp dt is approximately equal to m dv dt if gamma is less than the speed of light. If gamma is less than is approximately equal to 1. So we have approximately equal to its mass times its acceleration. So it's going to have an acceleration inward. So an accelerated charge radiates. And what happens when it radiates? Well, you won't be surprised to learn that that electric and magnetic fields actually carry energy, because if a field acts on some other charge, that charge starts moving in that direction and picks up kinetic energy. So it gains kinetic energy. Where did that kinetic energy come from? It came from the field. So this charge in this orbit should be radiating electric fields, which radiative electromagnetic fields carrying away energy and momentum, and therefore it should spiral down into the nucleus, losing energy and eventually just sit on top of the nucleus. So why doesn't it do that? Well, the answer is an interesting one. It's that if this were a classical system, that's what would happen. But because these are very small particles, we know from last semester that the available energy values of k plus u to a particle of this kind are not infinite. So if this is our potential energy curve, this is energy, and this is distance. We found that there are only certain values of k plus u that a bound system, a small system, could have. So this is k plus u. And what happens is that when an atom like this, a hydrogen atom, is in its ground state, is there's no lower state for it to go to. So there's no way for it to radiate and lose energy and drop to a lower energy level, because there's no lower energy level to go to. And so in fact, an atom is actually stable and the electron doesn't radiate away all of its energy. All right. So we hinted that there were other kinds of waveforms. We wouldn't necessarily have to just make a pulse. And one thing we can think about is, what if we had a charge that was connected to a spring-like chemical bond or something like that? So it oscillated up and down sinusoidally. Well, you can probably see without going through the math, although we can go through the math, that it's going to be accelerated this way, and then that way, and then this way, and that way, as its momentum changes. And so, in fact, it's oscillating sinusoidally. And so it could actually produce radiation that also is oscillating sinusoidally. So let's see what that might actually look like. So let's go back to the Python. And so if we had, so here's an antenna, basically. It's a piece of metal in which we're going to run a sinusoidal current. So we're going to have electrons going up and then down and then up and then down and then up and then down. And so they'll oscillate sinusoidally, and what it should happen is it should produce electromagnetic radiation coming out of this antenna that also oscillates sinusoidally. Now we're just showing the electric fields here, and we're only showing it along one plane because it would just get too horribly visually cluttered to see anything. But if we drive the electrons up and down, they're going to accelerate one way and then the other. And so an observer in this plane, perpendicular to A, would detect sinusoidally oscillating electric and magnetic fields, which are varying. So if we put a cursor at one location to see what an observer would see, it'd see up and then down and then up and then down, the magnetic fields would be changing also. So Kendra and John both ask, can electrons in upper energy levels drop to lower energy levels by emitting radiation? Absolutely, that's how it works. And we talked about that last semester, although we were talking about radiation as individual photons packaged in little packets. So we get, when one electron drops, it emits a pulse of this radiation that is a photon. Now it turns out, interestingly enough, that these photon pulses of radiation actually do have this sinusoidal wave-like character. So even though it's a particle, it's a wave at the same time. It has both particle-like and wave-like character. But this is exactly the process we talked about last semester, where a quantum system in an upper energy level could lose energy and drop to a lower energy level by emitting photons. And now we are making the connection between this quantum model of emitting photons and the classical model of emitting electromagnetic radiation, and seeing that we need pieces of both of these models really to understand what's happening. Because for one single electron dropping down to a lower energy level and emitting one photon, we're getting one tiny pulse, but if there's a system that has a mole of hydrogen and excited energy level, and all of these atoms are decaying down to lower energy levels, we're emitting lots of photons, and what it ends up looking like is one of these sort of continuous waves composed of lots of individual photons. So you're making exactly the right connection. And what we're doing is kind of bringing these two models together at this point. Okay, so let's look at a slightly simpler looking example here. So here's a sinusoidal wave traveling just in one direction from several sources. And you can see that there's a here, let's zoom in a little bit. There's a red arrow. So you can see that there's variations in both space and in time here. But if you look at just the red arrow here, so we've got this one observer, we see that an observer standing here would see a sinusoidally oscillating electric field. It oscillates up and then down and up and then down. The magnetic field also oscillates back and forth, back and forth. Yeah, the photon is indeed, so the photon is, in some deep sense, composed of electric and magnetic fields. That in a very deep sense is what the photon is. It's a little packet of electric and magnetic fields. So, and the photon, yes, the photon would be that pulse of E and B could be one photon or more than one photon or more than one photon emitted by a particular atom. So let's just yeah, it's cool, isn't it? It's interesting how these classical and quantum models come together, and then it turns out we need both ideas. Because in fact, the energy of a photon, last semester we talked about photons having different energies depending on the energy level spacing, right? But it turns out that the energy of a photon is related to a property of the wave-like nature of the electric and magnetic fields making up the photon, so that here, let me, there. So that what's called the wavelength, which is and I've paused this sinusoidal wave so we can look at it. The wavelength is defined as the distance from one peak to the next peak, or one dip in this case to the next dip. So this green marker here is the wavelength of the radiation here. So the energy of a photon is related to the wavelength of these electric and magnetic fields that are composing the photon. And so a shorter wavelength is higher energy, and a longer wavelength is lower energy. So we said blue photons have more energy than red photons. Well, blue photons have a slightly shorter wavelength to this oscillating electric and magnetic field character of the photon than a red photon. And so it sort of all comes together here. More waves, more photons, more energy. That's absolutely right. In our classical model, the energy in a field is proportional to the magnitude of E squared. In the quantum model, it's just proportional to each photon has a particular energy, and the total energy is proportional to the number of photons that are coming out in our wave. Yep, but more waves, more energy. So next Tuesday, we'll pursue this topic a little bit more because I'd like to talk about an important idea, which is how these electric and magnetic fields affect matter. You know, how do they interact with matter? And how do they interact with matter like your eye, for example, or how can you see the computer screen? How can you see a piece of paper? We know that computer screens emit light, which we now know is electromagnetic radiation, but a piece of paper doesn't emit light. If you turn off the lights, you can't see it. So how do photons interact with matter? And we'll talk about that next time. Okay, thanks guys, good work today. We'll try to wrap this all up into a kind of coherent package on next Tuesday.